Now that you know how to convert between binary and decimal numbers, we're going to look at a new number system called the hexadecimal number system. Hexadecimal is base 16, which means it's an even bigger base than the 10 that we're used to. And the reason that it's valuable is because since 16 is 2 to the 4th, it allows us to write binary numbers in a more condensed way. So in order for you to understand what I mean by that is I want you to open a terminal. So the way that you do that is hit Command space, that brings up your Spotlight search. If you just start to type terminal, it'll pop up, just hit enter, and you'll get a window that looks like this. Okay, your prompt here will probably be your username instead of mine, but what I want you to do is we're going to start up Python and look at how we can use Python to explore some of these different number systems. So Python 3 is what you want to type because we use Python version 3. If you hit enter on that, it'll bring up what's called the Python shell. And this is where we can type in Python commands and have them execute right away for us. And one of the cool things we can do in Python is to actually work with these different number systems. So, for instance, if I want to know the binary value of the number like 3, let's say, right? I can type bin 3 in parentheses. It's important that you use the parentheses. That's a function that's running that turns the 3 into a binary number. And you can see it gives me back 0b11. Now the 0b just means that that's a binary number, so it's not really part of the number itself. The 11 is the binary number. And then take a look at that, make sure you understand the 11, right? It's not 11. That first 1 doesn't represent 10, it represents 2. So that's 2 plus 1, or 3, right? 2 and 1 is 3, okay? Now, even a number as small as 3 required 2 binary digits to represent it. What if I wanted to represent, a larger number in binary? What if I wanted to represent 1,000 in binary? Well, let's look. Binary, 1,000. That's the number 1,000 in binary. How many digits does that take up? Well, 10 digits to represent the number 1,000. And so you can see binary digits are really kind of cumbersome for people to have to use. And so what we use are hexadecimal a lot of times because it's a lot more compact. And yet it still preserves the binary digits, and you'll see that in a minute here. Okay, so let's look at that hexadecimal number system. In the hexadecimal number system, again, the only difference is the place value, right? We're used to place values of 10, binary has place values of 2, hexadecimal has place values of 16. So let's look at the number 245 in hexadecimal. Okay, the 5 is 5 times 16 to the 0, which is 5 times 1, which is still just 5. The 4 doesn't represent 40, as it would in decimal, but it represents 4 times 16 to the first. And 4 times 16 is 64. And likewise, every time we move up a digit, we move up a power of 16. And so this number, 245 in hexadecimal, actually represents 581 in decimal. Now the question is, how do you know when you're working in hexadecimal versus binary? And the way that we know is we have these prefixes for these other number systems. So if you see OX in front of a number, that's hexadecimal, just like OB was for binary. And those O's, those are actually zeros. So 0X and 0B, not the letter O. So 0x245 means that's the hexadecimal number for 581. So how do we represent if we have a base 16? That means the digits have to go all the way up to 15, right? Just like the digits in base 10 go up to 9. So we don't have digits beyond 9 because in base 10 we just move over one more place value. Well, in hexadecimal, the way we account for that is we use letters for the digits. So the 0 through 9, those are the same digits and they represent the same values. But when we get to 10, we don't want to move to the next place value because we're in base 16. So we represent 10 with the letter A. Okay, and so when you see that in hex, that's not an A, really, it's a 10. 11 is B, 12 is C, and so on. We go all the way up to 15 because when we get to 16, we move to the new place value. Okay, so you might see some strange looking numbers that have letters in them, but they're actually numbers. Converting the other way is actually easier. So if we want to convert the number 4A7E in hex to decimal, well, we just use our place values. Okay, the 4, which is in the 16 to the third place, right? 16 to the 0, 1, 2, 3. We just multiply that out. 16 to the third, if you do that on a calculator, you get 4,096. You multiply that by 4, you get 16,384. And we just likewise move through the number. Now here the A, right? Remember A means 10. So this is 10 times 16 to the second, because it's in the 16 squareds place. 10 times 256 is 2,560. And we go all the way down. And so we can see that the number 4A7E in hex represents 19,070 in decimal, right? And that's really compact. It's actually even more compact than decimal. It's only 4 digits. If you wanted to represent this number in binary, well, let's see what would happen. Over here I can type in my Python shell the binary value of 19,070, and it's this huge binary number, which is really inconvenient to write. And that's why we use hexadecimal. It allows us to work in a number system that is close to what binary is, but not as cumbersome. So you might say, well, why is hexadecimal close to binary? And the reason has to do with the base. The base is 16. And so in the next video, we'll look at converting between hexadecimal and binary and how that works.